So without further ado, I think it's my pleasure to introduce our speaker today, who's Professor Anna Mavrogianni. She's the Professor of Sustainable, Healthy and Equitable Built Environment at the Institute for Environmental Design and Engineering at the Bartlett at UCL. She's an expert in indoor environmental quality, building energy retrofits and climate change adaptation of the built environment, with a focus on overheating and air quality exposure of vulnerable populations. She was the principal investigator of the Aspire project funded by EPSRC and a member of the UKRI Clean Air Network, HECIAM. It's a great pleasure to have you along, Anna, and to hear your presentation. She's going to talk about indoor environmental quality in UK schools in the context of climate change, mitigation and adaptation. It's hard to think of a more topical and interesting question at this point. So over to you, Anna. Please share your screen and take it away.
Can you say it full screen?
Yes, I can. Perfect.
So thank you so much, Paul, for the introductions, and to Kat and the Tapas Network for inviting me to give this talk. I have to say apologies to any participants who might have seen some of the slides before, because I gave a similar presentation back in October as part of the Breathing City network. So I'm going to talk about the Aspire project, which was an EPSRC funded project that was completed in July last year. And the focus was very much on this tension between the need to reduce our carbon emissions in the school sector, but also to mitigate climate change, mitigate overheating risk, and improve indoor environmental quality. So I will present a school building stock modeling framework that we developed in the context of this project. So this is just an outline of what I'm going to talk about. So first, the background and motivation for this work. Probably I won't go into much detail because I guess the Tapas Network members and a lot of the people attending today are familiar with these challenges. And then I'll take you through the development of the school building stock archetypes, some of the initial indoor environmental quality modeling results, and just a caveat here that we have primarily focused on overheating and indoor air pollutants. And then some of the work that my colleagues from the London School of Hygiene and Tropical Medicine have done on health impact assessment and asthma in particular. And then I led with an outline of the multi-criteria decision analysis framework we have been developing. So what is the challenge? So as Paul said, it's a very timely topic. So school children spend almost 30% of their life at school, around 70% of which is spent inside a classroom. And we know that there are established relationships between poor indoor air quality and excess temperatures, and very negative impacts on the learning performance, as well as the health and well-being of school children, and in some cases also the productivity and the comfort of staff. So there are established relationships between poor quality, in particular traffic-related pollutants such as nitrous dioxide and particulate matter, with a series of acute adverse health and learning effects. And we also know that children have a limited ability to thermoregulate and therefore could be potentially more vulnerable to excess heat exposure, and as well as high indoor concentrations of CO2. And these are linked with negative outcomes for concentration and cognitive performance, therefore negatively affecting educational attainment. At the same time, the school building sector is seen as a great opportunity to reduce carbon emissions in the UK and help meet national targets for climate change mitigation. So school buildings are responsible for around 15% of the country's public sector carbon emissions. And often energy is the largest non-staff cost, and it can be a significant portion of a school's budget. And of which space heating is the most important component. And at the same time, they tend to be, as a building stock, they tend to be quite a homogeneous stock. And therefore, they offer significant opportunities for energy use reductions because occupancy activities, equipment use are relatively homogeneous. And I have to say, from most of my research to date, before the Aspire project had focused on the housing stock, so building stock modeling for the housing sector, where again we see homogeneity being quite important in terms of implementing or assessing the impacts of retrofit for carbon emission reduction. So schools have some similar characteristics in this context. At the same time, climate change will pose an unprecedented challenge to the built environment, our communities, and there are parts of the population that are more heat vulnerable and will be disproportionately affected. So on the right there, you can see some of the headlines from last summer's July heat waves, where temperature reached, I think, 40 degrees. And I think this really increased awareness about the importance of dealing with heat. And there was a lot of discussion about school closures or changing uniform requirements and so on. So the school sector were specifically affected. As we know from epidemiological evidence, the very old, people with comorbidities, but also the very young are likely to be negatively affected during a heat wave. And the main challenge we are experiencing is this lack of a whole systems approach. Quite often we have net zero targets, guidance, standards being developed, but the focus is very much on the space heating demand of schools, and less so on indoor air quality as well. And I think this is to be expected because the UK is a heating-dominated climate context. So most of the buildings have been developed in order to maximize solar heat gains and reduce space heating needs in winter. But most of the buildings, including schools, are not well prepared to deal with warmer weather. And the issue there is that some of the energy retrofit measures that are likely to be implemented in the context of net zero targets are likely to lead to unintended consequences for indoor environmental quality by trapping indoor air pollutants as well as heat. So this is the kind of the conflict that we set out to explore in the Aspire project. And I'd just like to mention some additional challenges for urban schools in particular, and schools located in perhaps the most socially deprived neighborhoods. So as we know, in urban environments, indoor overheating effects will be magnified because of the urban heat island effect. And at the same time, heat and future climate change, as well as air pollution, is likely to lead to an exacerbation of inequalities. So on the one hand, we have evidence showing that children living or attending schools near high traffic density roads are likely to be more exposed to pollution, and this is possibly linked to socioeconomic factors and underlying inequalities. And these higher pollution levels could possibly also limit the potential for cooling through ventilation. And at the same time, schools in more deprived areas during a heat wave, they might not have the means to cope with excess heat indoors. They might not be able to afford emergency measures of installing fans or adjusting the environment, or more long-term planning, and therefore they might be faced with closures in the future. So again, exacerbating underlying inequalities and affecting educational attainment. So this is very much an area I'm interested in. So the Aspire project, as I said, was an interdisciplinary project funded by EPSRC, and it was a collaboration between us at UCL, the Institute for Environmental Design and Engineering, and colleagues at the London School of Hygiene and Tropical Medicine. We had an excellent set of project partners on our advisory board. So we started in 2022, which was at the beginning of the pandemic, unfortunately, which meant that a lot of the activities, the stakeholder engagement workshops, etc., that we were planning to carry out, unfortunately had to move online or converted into online surveys. So we faced some delays due to COVID, and we received a no-cost extension until mid-July. And naturally, some of our papers are still under review, so we are still finalizing some of the outputs from the project. So the overall aim of the project was to address this knowledge gap that I was outlining earlier. So how can school buildings achieve low carbon emissions whilst at the same time maintaining high indoor environmental quality that enhances learning and health? So with a focus again being on heat, overheating risk, and indoor air quality. And I guess our ultimate aim was to create this toolkit that could be used by stakeholders to assess the relative impact of design operation strategies on these factors. So our target audience was policymakers, as well as possibly designers, people involved being responsible for the design, retrofit, and provision of healthy school buildings, healthy and low carbon school buildings. So this was translated into these 5 objectives, each of them linked to a specific work package. So the first step was to carry out a literature review meta-analysis of existing data published at the time. A lot of additional research has emerged since we started with this work package. But our focus was very much on these relationships between classroom indoor air quality, temperature, and cognitive performance. And the second aim and a second objective and second work package was to analyze existing databases of the school building stock in order to build UK school building stock archetypes in a format that would be suitable for building performance analysis. The third objective was to quantify the exposure of school children to air pollutants and temperatures under a range of energy efficiency scenarios using dynamic building performance simulation. Also looking at different climate change scenarios. The fourth objective and work package, which was undertaken by colleagues at LSHDM, look at the health impact and cost effectiveness analysis for the same range of scenarios. And last came the multi-criteria assessment framework that combined all of the information produced in the previous work packages through input from stakeholders and assessment of the performance of different scenarios, interventions as we call them, across a range of criteria that were defined and weighted by stakeholders. So this diagram here visualizes the project structure. So at the initial stage, we had this detailed examination of the literature and the development of our school archetype library. The core component, and I guess the one that took the longest, was the dynamic building performance simulation part. And this then fed into the health impact and cost effectiveness analysis. But I have to say that the fifth part, the stakeholder engagement knowledge exchange, that ran across the project. And again, I would like to thank our advisory board, because they really fed into the development of the various retrofit scenarios that we tested. So that was really, really helpful. So these are some graphs from the literature from Mavrogianni et al. Demonstrating that relationship between temperature, CO2 concentration, and relative performance of students in various academic tests. Most of the underlying data comes from the European context, from a context relatively similar to the UK one. So these established relationships fed into our own calculations, where we try to quantify the impact of CO2 and temperature on performance in subsequent calculations. And this is the analysis that we did of the PDSP and DEC databases to which we had access. So you can see there the proportion of secondary and primary schools in the database across regions, across DEC, and the proportion naturally versus mechanically ventilated schools. Again, the majority of schools in the UK are naturally ventilated. So following the analysis of the PDSP database, the Property Data Survey Program database that was made available to us by the TFE, we developed these very simple archetypes. We call them seed models, based on 5 construction eras. And these construction eras were aligned with the introduction of different school building programs or changes in the building regulations. And this also reflect maintenance needs and life cycle expectations. So each construction era was associated with a typical geometry, a typical build form. So we had pre-1919, interwar 1940s to 60s, 60s to 70s, and post-1976. We didn't have a representation of more recently school buildings, but this is something that we potentially look at as part of future work. We looked at the classroom level, so our unit of analysis was the individual classroom across those 5 construction era archetypes, a number of locations that were determined by the availability of weather files and different orientations. And we also ran simulations in Energy Plus, use fixed ventilation as well as natural weather-dependent ventilation scenarios. So this, I guess, illustrates the overall development of our building stock model. So seed models, again, emerging from the PDSP database, then developing the specific archetype models with more detailed geometry, and then carrying out all of this feeding into the Energy Plus calculation engine with some post-processing analysis being carried out in Python. So our inputs were the geometry as well as building fabric characteristics as a function of construction aids that we derive from the literature. And I will show some tables with these, summarizing those inputs later on. So the main outputs were indoor CO2, PM2.5, NO2 entering from outdoors to indoors, energy use, dry bulb temperature and ventilation rates. And then through post-processing, using those established relationships from the literature, we attempted to estimate their impact, the impact of those indoor environmental metrics into cognitive performance. We assessed overheating using established overheating criteria such as Building Bulletin 101, CIP-CTM 52, and other outputs. And just to clarify here that I guess one of the limitations is that we didn't really include indoor sources of pollutants such as PMs or VOCs, but the focus was very much on traffic-related pollutants and indoor internally generated CO2. So we also tried to validate our model outputs. So we use the display energy certificate database for the same school. So we matched the some of the model schools with schools in the display energy certificate database. And we compared our energy use predictions against measured data. And we found good agreement, showing this energy in buildings paper led by my colleague Gary Schwartz. We found good agreement between simulate and measure energy use intensity for naturally ventilated schools, for mechanically ventilated schools, less so, but it was a satisfactory agreement for naturally ventilated schools, which were subsequently our focus. So this is from a Buildings and Cities paper led by Duncan Grassi. So here we presented in more detail our modeling framework and the different scenarios, interventions that we tested. So we focused on the English primary classroom stock model containing 111 archetypes. So we start with the base case scenario, different terrain, city, suburbs, countryside, different geographical locations, again linked to a different weather file, different construction eras. We included the potential for the building to have been modified or extended, and the focus was very much on natural ventilation. We also included different orientations. And we ran simulations for the current climate, 2050s and 2080s, different emission scenarios. And then we looked at a number of energy retrofit scenarios and overheating mitigation, or shall we say indoor environmental quality improvement measures. And the performance metrics were again overheating, energy use for heating in winter, and indoor air pollutants. And the aim was again to look at this conflict between trying to reduce space heating demand in winter whilst at the same time not jeopardizing thermal comfort in the summer or air quality. So these are some of the assumptions we made for the different construction eras, and on this we also received quite useful input from our reviewers. So again, of course, these are estimates and informed assumptions, often based on expert opinion on the different building fabric characteristics of different construction eras. So they're likely to be associated with a certain level of uncertainty. Apologies. And this is a summary of the measures that we tested in the specific paper, the building fabric retrofit scenarios. So our aim throughout the project was to test some of the more ambitious kind of EnerFit level scenarios, but also the ones that were more realistic, as well as kind of building regulation compliance. And we also tested the use of external shading, because literature, both monitoring and modeling studies have demonstrated that external shading can be one of the most effective ways to reduce overheating risk across building types. It's more effective to block solar radiation before it enters a building, and then you have to deal with it. So yeah, again, a summary of the measures for overheating mitigation. We also use model internal shading as well as nighttime cooling. Internal shading, possibly a more easy to implement measure, so that we thought it was important to look at. And nighttime cooling, again, it's often proposed as an effective measure, but as we know, it comes with some limitations. It might not be possible because of security concerns, especially if we're at the ground floor, or if we look at the if there are security concerns, especially if it's in an urban location. So these are some of the modeling outputs for the warmest week in the weather file we're examining. So performance of the indoor environment under different retrofit and indoor environmental quality management scenarios for a west-facing London classroom, so kind of a worst-case scenario. Again, in terms of comparison validation of our outputs, we found that some of the temperature outputs were in good agreement with those observed in the Symphony project for West Europe classrooms. And what we observe here is that the base case and the retrofit only scenarios do have a problem with overheating in the future. So I think this really highlights the need to implement overheating mitigation measures alongside any energy retrofit strategies. So a range of retrofit and passive cooling measures combined can mitigate against overheating a lot, although it's likely that as we move towards the future, towards more pessimistic scenarios of climate change, emission scenarios, or as we after the middle of the century and as we approach the 2080s, it's likely that we might need to use some form of active mechanically driven cooling. And this is something that is in agreement with studies, modeling studies we've done, predicting overheating risk and the physical potential of passive cooling strategies in other building types, other work we've done in care homes or housing. But I think it's really, really important to emphasize the need to prioritize those passive cooling strategies because they will still limit the need for active cooling and hopefully reducing cooling loads and associated possibly electricity costs if we talk about air conditioning. And although we didn't find a single solution that had positive effects across the different building performance metrics we're analyzing, night ventilation overhangs were found to be particularly effective across the school stock. Again, with the caveats associated with night ventilation for some of the urban schools. So following this step, we try to translate those outputs into metrics that could feed into both the health analysis part as well as the MCDA. So we looked at the variation of metrics across the climate scenarios and different orientations. And we tried to carry out the normalization process so that they can then feed into as distinct criteria, so they could feed into the MCDA process. So on the health impact assessment, so that work was led, as I said, by colleagues at the London School of Hygiene and Tropical Medicine. So first they carried out a review of existing evidence on air pollution-related health outcomes for children, and then they focused on a evaluation of health outcomes in the short term, specifically focusing on asthma for school children. So they use model levels of NO2 under the 2020s scenario from Energy Plus from the work package 3 modeling, data on regional asthma incidence from a global burden of disease study, and census and mortality data from the Office for National Statistics. So this is from a conference paper, and there is also an upcoming journal paper as well that hasn't been published yet. So they assess the impact of the same retrofit scenarios on potential childhood asthma that could be attributable to indoor NO2 across the various regions. So they looked at the same energy efficiency strategies, and they compared the base case and retrofitted scenario against very ambitious EnerFit levels of retrofit. And the analysis was based on some previous work they have carried out for NICE, as well as the HIDE model that was developed for BASE. So what they found was that the highest indoor concentrations were estimated in the Thames Valley region, including London, in particular in older school buildings, whereas the lowest concentrations were found in newer schools in Wales. So I think that's possibly, my interpretation of this output is that this is probably a combination of the impact of the building fabric characteristics and the building form, as well as the location and the levels of outdoor air pollution. And they also found that improving energy efficiency essentially increases the air tightness of school buildings and reduces the air change with the outdoors, therefore reducing the amount of external air pollution entering school buildings. So what they found was that asthma incidents were reduced by increasing the energy efficiency of schools. Again, the limitation there is that we didn't model internally generated pollutants. So I think a future study should really look at this balance between internally and externally generated pollutants and how energy efficiency could modify that relationship across the same energy efficiency scenarios, regions, and school building types. Just checking how I'm doing for time. So yeah, last I'll just talk about the MCDA framework. So the MCDA framework, led by Dr. Zaid Chalabi, comprises of 5 core elements: a set of policy options. In our case, that was related to the energy efficiency scenarios and the other building level interventions that we were testing. Second, a set of criteria for assessing and comparing the options. These are usually defined by stakeholders. In our case, we approach our advisory board and we ask them to help us define this small number of criteria. A set of models to determine the impact of each policy option against each criterion. So that was through our modeling work. And a very important part was eliciting weights that assign the relative importance of each criterion. So that part would have been carried out in a very interactive stakeholder workshop or a series of workshops, which unfortunately weren't able to carry out face-to-face. So instead we had to modify our study design and carry this out as an online survey. So essentially, we asked the participants of the survey to rank the criteria that were defined by our advisory board based on their importance. And last, we integrate the impacts and the weights to determine the overall value of each policy option across the defined criteria. So this is a visual that kind of shows how the MCDA framework can work quantitatively. So we do rely on both models as well as expert opinion, and we rely on, again, the stakeholders, their inputs in terms of ranking the criteria based on their importance. And the final scores are a combination of all these inputs. So this summarizes the results of the online stakeholder survey. So that was carried out, unfortunately, in the middle of the lockdown in the summer of 2021. We had around 110 respondents with 115 valid entries. And I think some of the sectors were overrepresented. I think we had a significant number of people from school communities, which was great. And I have to highlight the limitation of this approach, that it is a snapshot in time. And we thought at the time that perhaps the people that participate in the survey, as it was in the middle of the COVID pandemic, were quite health conscious. So other priorities such as carbon emissions were perhaps further down their priorities at this given point in time. So I think it would be worth repeating the survey and the calculations to see what impact this might have on the final outputs of the MCDA process. So student learning performance came at the top by all groups, so that including non-teaching school staff, teaching school staff, and other professionals working in the education sector, construction industry, and then we had a number of policymakers, people from both national and local government. What I found interesting was that the reduction in school building carbon footprint was rated relatively higher by construction industry professionals. Again, the ranking and the priorities reflect the priorities of each sector, which I think is really interesting. And I think it highlights the importance of having everyone around the table. So this is further modeling work we did in order to produce the modeling inputs for the final MCDA framework. So again, work led by Duncan Grassi, published quite recently. So he expanded the modeling work I presented earlier, including both primary and secondary school classrooms this time, and additional energy retrofit and indoor environmental quality improvement strategies. And a forthcoming paper will address how these criteria can be weighted using the stakeholder survey and combined with the MCDA tool to look at the performance of these pairwise scenarios across all of the criteria. And I guess what we found here was that in a way, because the emphasis of the stakeholders, what they valued the most was pupil learning performance, which was linked to low temperatures indoors and good indoor air quality. In a way, this penalized some of the scenarios that focused on the having a very energy efficient building fabric. So that was something really interesting, and we would like to explore this even further, looking at additional scenarios that perhaps offer win-win solutions that at the simultaneously improve building fabric performance for winter, but at the same time do not again jeopardize summer thermal performance or do not deteriorate indoor air quality. So in terms of future work, we have completed the MCDA framework, and we have a paper that is currently under review. And we would really like to incorporate additional retrofit and operational scenarios, perhaps looking at additional overheating mitigation technologies, and also incorporating the guidance that came out for COVID in terms of ventilation requirements. A key limitation, as I mentioned earlier, is the modeling of the lack of modeling of internally generated air pollutants, such as particulate matter or VOCs. So we'd be really keen to include this in future work. But I guess this approach is archetype based. So we're trying to represent the entire school building stock through a limited set of school building archetypes. So naturally, as we've seen with similar building stock modeling approaches for the housing sector, this can have quite a lot of limitations. And we now see a shift from archetype-based building stock models to the development of one-by-one models. And we've also been doing some work in this area. And last, for the climate change scenarios that we tested, we used the older UKCP, UK Climate Projections 2009 weather files that were available at the time. CIPSI now has a project and they aim to develop UKCP 18 climate change weather files. So we will be using these in future work. And these are some of the publications that I mentioned that describe the modeling inputs in particular in more detail. And yeah, hopefully we'll have 2 more publications out very soon. So thank you so much for listening. I don't know how I've been doing for time. Yeah. So yeah, I don't know if there are any questions.
Thank you very much, Anna. That was excellent and very, as I said earlier, very timely and apposite.
Thank you.
So thank you. We have some things in the chat that I'm trying to get to. I can't. For some reason I can't read the first one.
Yeah, it's a bit stuck for me as well. I can't
read the very beginning of the first one, but says, do schools have high temperature cutoffs at the moment?
Yeah, so there is the BB1 guidance.
At the beginning of it says you just showed performance up to 30 when we all know
that's right.
40 last year. So, and these high temperatures will surely sadly get more common. So then you can read the next bit or read it.
That's right. Yeah. Sorry. Yeah, it appeared now.
Yeah. Thank you.
Yes, indeed. So we used as I said, the UKCP09 scenarios. So in the future, once the UKCP18 scenarios will become available, we will start using these ones. Yes, it looks like some of the most pessimistic scenarios of warming are coming true, unfortunately. So we are likely to experience much higher temperatures than originally predicted. So we have the BB1 guidance, but I think it's worth revisiting those. Again, because indoor thermal performance depends on so many parameters that might not be easily linearly interpolated. I would be nervous about extrapolating some of the linear relationships that we might observe. So I think we need more up-to-date climate change scenarios and additional modeling work to see how that curve can be extrapolated, if that makes sense.
Yeah, and the follow-on question says, have you thought about trees, green infrastructure for cooling and pollution mitigation? Did you consider that as a possible thing to consider?
No, well, initially we did, and it was we wanted to include green and blue infrastructure because, as we know, they can have really positive benefits for overheating mitigation and outdoor thermal comfort as well. We did not include them explicitly. We would really like to expand some of the modeling to look at the impact of the urban heat island and use more localized weather files. But at the time, I think we're trying to stay at the regional level, and because of the computing time required to run some of the simulations, we were in fact trying to group some of the regional outputs. But this is something that we would really like to look at in the future. And I think there are also additional benefits of green infrastructure, such as, if it gets too hot in the classroom during a hot spell, some classes could even move outside. So I think there are benefits beyond indoor temperature modification.
Yeah, and certainly in the MAGIC project that I was involved with, where we were looking at the impact of green and blue infrastructure on cities, we have clear data that that parkland, for example, is significantly cooler than the surroundings in terms of urban heat island. So, I mean, what isn't clear, I guess, is, how big a parkland you need to make a big impact on, is a couple of trees enough? Probably not. But I think it's a very interesting aspect to explore.
Indeed.
Following on from that, Iman says, fantastic presentation, which I agree. How do you think the prevalence of HVAC heat pumps will change the landscape regarding school heating and cooling in the future?
Yeah, so HVAC and heat pumps in particular used for cooling was something we discussed quite a lot. It wasn't something we modeled specifically. I do think it's going to change the landscape in particular because there is that push now for heat pumps. And I think it's really important to understand the relationship between heat pump performance and building fabric efficiency as well, in particular for heating. But as I said earlier, it's also important to adopt the building fabric first approach, prioritize passive cooling strategies because it will reduce the cooling loads that we might be faced with in the future. So, and I think that's really important because, again, if we're talking about, school budgets and what schools might want to prioritize, again, some of the schools in the possibly more deprived areas might be the worst affected. And as I said, faced with closures if they can't afford to run
exactly
an active system.
Yeah, and in fact, that follows on to the rest of the question, really, which who says that he talks to energy managers who have to make difficult decisions regarding funding. And what, did you encompass those kind of issues when you were doing your research?
Yeah, so this is something that I have said for a very long time, is that we need to reframe overheating and air quality as energy and productivity issues. So I think they're very often framed as comfort issues. And I think there is a risk there that they're not prioritized enough. So yeah, if we need to install active cooling systems at some point, because the stock is currently primarily naturally ventilated, we don't think about the need to improve summer thermal performance as a cost and an energy problem, which is perhaps why we don't see it as a priority. And until recently, this was perhaps not reflecting the building regulations. So again, it wasn't a compliance issue either. I really think that we need to frame this as a potential risk down the line, something that will increase our energy use, carbon emissions, and fuel costs. But also in terms of energy managers or other stakeholders involved in those decisions in the school sector, I think we also need to perhaps emphasize the importance for cognitive performance of children, because as you saw in the survey, that came at the top of the priorities for all of the stakeholders that we surveyed. So I think that says a lot. And it's also a productivity issue for the teaching staff as well. So I think we just need to change the language, the way we talk about those issues. And hopefully this will lead to informed decisions in this area.
Right. And from Sarah, who also says fascinating talk. So in SAMI, the project that we're putting carbon dioxide monitors in 1,500 schools, we want to relate this to their building type, among other things. And so is there a database of the archetypes that you had that we could access to, linked to a unique school number, for example?
Yeah, thanks so much for this comment. And in fact, I have been meaning to get in touch with the SAMI team for quite a while. It's been in my to-do list for a long time now. So I'll be in touch if that's okay. We have now moved from the PDSP database to the CDC database, which is a bit more advanced, I believe. And I do think, there might be ways to do this kind of matching, either through archetypes or other information. So that would be fantastic. So I'll be in touch if that's okay.
Right. And so can I add my own question? You talked a lot about doing things with buildings and so on. Did you talk at all about changing behavior? So, for example, maybe extending the summer break or changing school hours so that kids were not in school in the hottest part of the day, things like that? Is that something that you considered, or is that outside the remit?
We did discuss it, and I think Duncan is online as well, so you might recall. We had a lot of discussions about the proportion of the day that we were modeling, I think in the end, we just decided to stick with what the BB 101 criteria
Right.
define as occupancy. But yeah, we had a lot of discussion because, as we know, a lot of schools have after school clubs, or they might be used for community community events outside the core opening hours of a school. In fact, I was part of another project that looked at design lessons learned during and post-pandemic for schools. And one of them was opening up to the community, using the building as much as possible and building those relationships. So we didn't really look at this different, shall we say, behavior operation changes in a lot of detail in our modeling. Again, this is something that we could easily implement. I think we primarily focus on different window operation.
Right, sure.
With your scenarios, yeah.
Yeah. And well, since Duncan is on the call, is there anything you wanted to add, Duncan?
Hi, Duncan. Sorry to put you on the spot.
Sorry,
Yes.
sorry, it's okay. I was, hello, can you hear me now?
Yes.
Actually, yeah, I was just typing out a response there to what Anna was saying, that the BB 101 overheating is limiting us a little bit, in the sense that we assume the school is occupied at certain times, but we do have students currently looking, master's students actually, but potentially PhD students in the future who look at, we're hoping to get more of the effect of the use of school out of hours, because obviously part of my actual PhD rather than Aspire was the fact that schools are being used obviously in the evenings, and what impact that might have on overheating and things like that if they are being used. So yeah, actually there's lots of paths it could take actually in the future, and we're not really. I mean, that's the thing. It could be look at overheating in terms of what causes it from occupancy point of view or from physical building point of view as well.
Yeah.
So.
Yeah, thank you. Well, so I think that brings us to the end of the questions. It just remains for me to thank Anna again for a really fabulous talk, and it's really work. And as I said earlier, I think it's a very timely project, and I think it's only going to get more important as climate change progresses. Unfortunately, I think we're going to see more and more of these issues raising. So it's great to have a team like yours actively involved. Just to say to everyone, thanks for coming. We're having a break next week because it's half term, but we'll have our final seminar in this series on the 8th of June, Thursday, the 8th of June, so 2 weeks from today, with Rowan Ryrie and Claire Larkin from Parents for Future UK, who'll talk on engaging parents as part of school communities. So I think this will be a rather different focus of the things that we've been talking about, but actually something that we in TAPAS are very concerned about is trying to make sure that we speak to the constituents, and parents are obviously very important constituents in this whole business. So please come back and join us in 2 weeks' time. And until then, have a good couple of weeks. And thanks again, everybody. Bye-bye.
Thanks so much. Thanks.
Okay, bye-bye.
Bye.